In this video, we're going to talk about standard W6 interference. And coming out of this lesson, what I would like you to be able to do is to be able to add waves together, identify factors of interference, and just understand what constructive and destructive interference are. You should have this in your notes, so let's start talking about W6. In introducing interference, I had to talk about this term superposition, which is a term you might have heard before either in math class or in some other setting. What superposition basically means is if two things are affecting something in the same spot, you basically take the effect of each of them and add them together. In this scenario, we're going to be talking about it in terms of waves. So when you have two waves that are propagating in the same area, and they're both causing some amplitude to the medium, you take the effect of the amplitude for both waves, and then you just add them together. When you add them together, you had to add them together as if they were vectors, though. And when I mean that they're vectors, I mean you don't just take their magnitudes and add them together. You have to assume that they have some positional aspect to it. So if one is pushing to up and one is pushing to the right, the effect would be as if you followed both of them one after another. We'll practice this in class. We're not going to practice this in the virtual lesson, but when you come back, we will be practicing adding waves together. So we add the amplitudes, and then this is an important piece when we talk about superposition of waves. When a wave meets in a medium, maybe they're heading in different directions, maybe they're heading in the same direction, whatever the case may be. When they superimpose on each other, you're just capturing it at one point in time. You're not looking at sort of what was happening before or after. We capture it in a spot in time, and we identify what's going to be happening to the medium by adding up their amplitudes. However, after the waves meet each other and pass by, they're unaffected by the fact that they were previously superimposed. So the medium itself is going to be taking contributions from both waves while they're both acting on the medium. But after the waves pass each other by, they're still going to be continuing on as if they had never met in the first place. So waves superimpose when they're on top of each other, but they don't affect each other by having superimposed in the first place. So now that we talked about what superposition is, there's one other thing I have to talk to you about before we could really get into wave interference, and that is wave phase. And I want you to think about wave phase as a way of telling what part of the wave that you've moved through. It's a reference. Every phase just identifies, are you at the start, in the middle of your wave, at the back of the wave. Remember that every wave is a moving oscillation. So every oscillation has to repeat itself over some pattern. So when you talk about the phase, it's just saying from one initial position till it goes all the way back through its total oscillation, how much of it is it through. And in order to identify how much of it is through, you have to be able to give it like a start and an end. So when we talk about wave phase, we're going to use the unit circle standard and say that we're going to impose one full wave over 360 degrees. If you're looking at this in your notes, you can see that, say, like at 0, which we consider the start of the wave has not yet begun to crest. It is at its initial position. As we get through a quarter of the wave, so we're one quarter through the wave, we're at 90 degrees, right? As you're half a wave in, you're at 180 degrees. As you're 3/4 at 270, and at 360, you're at 300. Why this matters and why we care about it is that if we're looking at trying to identify two waves that are superimposing, this wave and that wave are in the same place, right? But we don't have a diagram to aid us. We can say that we know the wave is cresting at 90 degrees, or that the wave is at its trough at 270 degrees. So we're able to identify whether the wave is pushing up or pushing down at a single particular point in time. Let's talk about the spots in the wave that are relevant. In wave phase, the 0, the 180, and the 360 degree spots are the spots where the object is at equilibrium. That's its rest position. When you're at 90 degrees, you're at the highest point, and when you're at 270 degrees, you're at its lowest point. So you're at the crest at 90 and at the trough at 270. This identifies sort of what wave phase is. I think it's helpful to look at wave phase by comparing how offset two waves are. So these next slides, they're not in your notes, but they do a good job of doing that. Now I have two waves here. I have a red wave and I have a blue wave, and you might be able to see the blue behind the red. These two waves are in phase, meaning that the red, they're cresting at the same time and they're hitting their trough at the same time. So I would describe these waves as in phase, or I would say the phase between these two waves is 0 degrees. Let's take a look at these two waves here. You have a blue wave and you have a red wave. You can see that the red wave starts a quarter of the wavelength down the blue wave, meaning that when the red wave is starting, the blue wave is cresting. And when the blue wave is cresting, or the red wave is cresting, the blue wave is at its equilibrium. And again, while the red wave is at equilibrium, the blue wave is at its trough. So every spot in this wave, the red wave is a quarter of a wavelength in front, of the blue wave. We would say the phase between these two waves is 90 degrees. It means that one wave is just a quarter of a wavelength in front of the other wave. In this example right here, if you were to think about it, take a moment and see if you can't figure out the red wave and the blue wave here, how far offset they are. And I hope that maybe you said that they're 180 degrees offset. The red wave was half a wavelength in front of the blue wave. And here we have these last two waves. The red wave is 3/4 of a wavelength in front, so that's 270 degrees. It's a way of telling how offset two waves are. Usually you only need to show one wave, so you can say, like, if a wave is half a wavelength, you'd say it's 180 degrees. Now that we've talked about wave phase, let's talk about constructive and destructive interference. If we have two waves and they are in the same frequency, they're in the same phase, they constructively interfere. If you look at this example, and this would be on the right of your notes, you'll see three waves kind of like stacked on top of each other. You'll see wave A, in the screen it's blue, wave B on screen is green. Now these two waves are both acting in the same medium at the same time. You'll see that the crests of A and B line up. So you have the crest in A directly over the crest of B, and you have the troughs of A directly above the crest for B. If we were to add the amplitudes together, you'd be adding this amplitude to this amplitude, you'd end up with what wave C is. And you'll notice that the amplitude of C is twice A and twice B, because A and B having the same amplitude, you would add those amplitudes together and you get a greater amplitude. When you add the amplitudes together and you add the troughs together and they're making greater amplitudes for the combined wave, we call that constructive interference, because they're adding together, they're contributing to the same amplitudes. If you looked at destructive interference, this is when the two waves, they have identical frequency, but now their phase is 180 degrees, meaning that they're half a wavelength offset from each other. If you look at these examples, you'll see that when the blue wave is cresting, the green wave is at its trough. And then if you look at the combined wave, if you added the amplitude which A is pushing up to the amplitude of B, which is pushing down, they would cancel each other out. That's why it's called destructive interference. In that interference, you'll see that the waves don't add up and that they constructively or destructively interfere. I'm going to show you some examples in a PhET simulation next, just for you to see some of this constructive and destructive interference in moving waves. And then we'll follow up this at the end, just talking about standing waves.